Hello everybody. Now we shall discuss about measurement of capacitance. Measurement of capacitance. The following bridges can be used for the measurement of capacitance. De-Satis bridge, modified De-Satis bridge, modified De-Satis bridge, sharing bridge. These bridges can be used for the measurement of capacitance. Before going to discuss about this De-Satis bridge, let us have the representation of ideal capacitor and practical capacitor, and let us discuss about derating factor or dissipation factor. Okay. Now coming to the representation of ideal capacitor. Ideal capacitor. Okay, here representation of practical capacitor. Representation of an ideal capacitor. Okay, representation of a practical capacitor. Okay, when two conducting plates are separated by an insulating medium, nothing but capacitor. This is one of the conducting plates, this is another conducting plate. Okay, two conducting plates. When two conducting plates are separated by an insulating medium, nothing but capacitor. Okay, this is the symbolic representation of an ideal capacitor. This is symbolic representation of an ideal capacitor. Okay, these two are conducting plates. Okay, in between these two conducting plates, you are going to have insulating medium or dielectric medium. Okay, so here the resistance of the dielectric medium is infinity. In case of ideal capacitor, an ideal capacitor has an infinite dielectric resistance. And plates, conducting plates, anyhow plates are made of metals. Okay, these two are conducting plates. Okay, these two conducting plates are having zero resistance. Okay, this is the symbolic representation of an ideal capacitor. An ideal capacitor has infinite dielectric resistance. Okay, in between two plates you are going to have dielectric medium. Okay, dielectric medium is present between these two plates. Okay, this dielectric medium is having infinite resistance. Okay, let RD is a resistance of dielectric medium, will be infinity. This will be infinity. Okay, coming to RP. Okay, conducting plates, resistance of conducting plates. Okay, let R is the resistance of conducting plates, then this will be 0. Resistance of conducting plates will be 0. Okay, so an ideal capacitor has an infinite dielectric resistance and plates that have 0 resistance. Okay, these two plates are having 0 resistance. Okay, that's why this is the symbolic representation of an ideal capacitor. Okay, dielectric medium resistance is infinity means no current will be flowing through capacitor. No current flows from this plate to this plate. Let this is plate A, this is plate B. Then no current is flowing from plate A to plate B. Okay, only displacement current will flow through the capacitor. Only displacement current will flow through the capacitor. Okay, when RD is equal to infinity means resistance of dielectric medium is infinity means no current will flow from this plate to this plate. No current will flow through this capacitor. Okay, only displacement current will flow through the capacitor. Okay, now coming to the representation of a practical capacitor. Representation of a practical capacitor. All practical capacitors, all real or practical capacitors, capacitors will leak current. Capacitors have leakage resistance. Leakage resistance of dielectric medium. Dielectric medium. And conducting plates have some resistance, some small resistance, anyhow that is very small. Okay, now coming to the representation of a practical capacitor. Two conducting plates separated by an insulating medium. Okay, now anyhow all real or practical capacitors are having leakage resistance of dielectric medium. Okay, that is resistance of dielectric medium is not infinity. In case of this, it is not infinity. It may be large, but it is not infinity. If it is large, if it is high, if this RD is high, if this high means small leakage current will be flowing through these plates. Okay, so it is having leakage resistance of dielectric medium. That can be visualized. That leakage resistance of dielectric medium can be visualized by connecting resistance in parallel with this capacitor. Okay, as this is parallel connected in parallel, so let me represent RP, this resistance by RP. Let me represent this resistance by RP. So this is RP. Okay. Now practical capacitors are having some resistance, anyhow it is very less, small resistance, okay, that can be visualized by connecting a resistance in series with this capacitor. As it is connected in series, let Rs is series resistance which is connected in series with this capacitor. This represents power loss in plates. This represents leakage current through plates. Okay, this represents leakage resistance of dielectric medium. This represents power loss in conducting plates. Anyhow, this is very small, very small, very small, nearly equal to 0. So you can also neglect, and roughly speaking, this is the representation of practical capacitor. Okay, strictly speaking, this is the representation of practical capacitor. So this will be Rp and this will be C. Okay, C. Okay. Now representation of a practical capacitor. Okay. Capacitor across resistor. See, Rp. Let this is Cp, as these two are in parallel. Now what we do is, for the sake of convenience, let me have an equivalent network to this network. Okay, let us have series combination of capacitor and resistance. Let this is Cs and this will be Rs. Series combination of capacitance and resistance. Okay, now this is an equivalent network to this network when this Zp, let Zp is the impedance of this network, let Zs is the impedance of this network. Okay, what I am doing is I am making both equal. Let us make both equal. Okay, Zp is equal to Zs. After equating both Zp and Zs, you are going to get Cs in terms of omega Cp Rp. Similarly, you are going to get Rs in terms of omega Cp Rp. Okay, let V of t is the voltage applied to this, I of t is the current flowing to this, V of t is voltage applied across this with an angular frequency of omega. Okay, what I am doing is, in order to get series equivalent to this network, I am making both impedances equal. If I make both impedances equal, then I can get series equivalent to this parallel equivalent, to this parallel combination. Okay, so now let me use this series combination. Now this will be the practical capacitor, representation of practical capacitor. Actual representation of practical capacitor is this one. Now what I am doing is, I am getting series equivalent to this parallel combination by making two impedances equal. Okay, even practical inductor, representation of practical inductor, you take representation of practical inductor, this can also be done like this. We can have if it is Rs, Ls, you can have Rp and Lp by making two impedances equal. Zs equal to Zp. Okay, you can get Rp in terms of omega Rs Ls. Similarly, you can get Lp in terms of omega Rs Ls. Okay. Now you take pure capacitor. Pure capacitor or ideal capacitor means no dielectric loss, no dielectric loss. Okay, then this is pure capacitor. Now let me apply voltage across this capacitor. Okay, let I is the current flowing to this capacitor C. Let V is the voltage applied across this capacitor. Okay, let Vc is the voltage across this capacitor. Now you can draw the phasor diagram. Let me take current as reference vector. Then voltage across capacitor lags current by an angle 90 degrees, or current leads voltage by 90 degrees. Now let us take practical capacitor. Practical capacitor. Capacitor means with dielectric loss. Okay, with dielectric loss. Dielectric loss. Practical capacitor or impure capacitor. Impure capacitor. Okay, now let us take series equivalent. R, this is C. Let V is the voltage applied across this series combination. Let voltage across this is let Vc is the voltage across this and Vr is the voltage across this. Okay. Now let us draw the phasor diagram. Let I is the current flow into this. Okay, now we take current as reference vector. Let me take current as reference vector. Then how can I draw Vr? Anyhow, Vr in phase with I. So this will be Vr is equal to I into R, is equal to I into R. How can I draw voltage across capacitor? Voltage across capacitor lags current by an angle 90 degrees. So this will be what? This will be Vc. Vc is equal to 1 by j omega c. Sorry, I into 1 by omega c. If you take magnitude, I by omega c. Okay. Now, how can I draw phasor V? Total voltage is the phasor sum of VR and Vc. Okay. So you can have phasor sum of VR and Vc gives VR and Vc gives what? V. Okay. Let delta is the angle between V and Vc. Let delta is the angle between V and Vc. Okay, then I'll do one thing. Okay, now okay, fine. let delta is the angle between applied voltage and voltage across capacitor. Okay, anyhow phi will be the angle between voltage and current. Okay, this phi will be equal to 90 minus delta. Okay, now let us find derating factor or dissipation factor. Okay, dissipation factor or derating factor or badness factor. Okay, here badness is reciprocal of goodness. Okay, what is mean by this goodness in case of capacitor? Goodness means how practical capacitor is close to ideal capacitor is goodness. Coming to badness, it is the reciprocal of goodness. Okay, that is, if dissipation factor is more means practical capacitor is not close to ideal capacitor. If dissipation factor is less means practical capacitor is close to ideal capacitor. Okay, so dissipation factor is equal to dissipation factor or D factor is equal to voltage across R by voltage across C, which is equal to I into R by this is I by omega C. Okay, otherwise I into XC, which is equal to IR by I by omega C, which is equal to omega RC is the dissipation factor, which is, this dissipation factor is nothing but tan delta, which is nothing but tan delta. Okay, here what is tan delta? Here what is tan delta? Tan delta is equal to VR. Okay, this will be VR, right? This will be VR. Okay, VR by VC will be tan delta. Okay, so VR by VC is tan delta, which is equal to omega RC. This is dissipation factor. Okay, dissipation factor D factor is equal to tan delta, which is equal to VR by VC, which is equal to omega RC. Now let us discuss about de-Sart's bridge. Now we will go for first bridge, that is de-Sart's bridge. de-Sart's bridge. C1, C2, R3, R4. Okay, let I1 is the current flow into this. I1 is the current flow into this. I3, I2, I4. Let E2 is the voltage across this, E4 is the voltage across this, E1 is the voltage across this capacitor, E3 is the voltage across this. Okay. Okay, here C1 is equal to capacitor whose capacitance is to be measured. Capacitor whose capacitance is to be measured is C1. Coming to C2, standard capacitor. Coming to R3, R4, non-inductive resistances. Non-inductive resistors or resistances. Standard capacitance, or you can also write standard capacitance. Instead of writing, you can write standard capacitance. Okay. Now, under balanced conditions, Z1, Z4 is equal to Z2, Z3. What is Z1? Z1 is equal to 1 by j omega C1. What is Z4? Z4 is equal to R4. What is Z2? Z2 is 1 by j omega C2. What is Z3? Z3 is R3. Okay. Both will get cancelled. From this, C1 is equal to C2 into R4 by R3. Okay. C1 is equal to C2 into R4 by R3. Okay. So, it is advisable not to vary C2. Okay, not to use variable capacitor. It is better not to use variable capacitor as it is having low degree of accuracy. Okay, that's why we use standard capacitor, fixed capacitor only. Okay, but in order to obtain balance condition, let us vary R3 or R4. Okay, so the balance can be obtained by varying either R3 or R4. Okay, so the balance can be obtained by varying either R3 or R4. The advantage of this bridge is, its simplicity. It is simple bridge. Okay, simplicity. The advantage of this bridge is simplicity. Coming to the limitations, it is not impossible to obtain balance condition. It is not impossible to obtain balance condition. Balance if both the capacitors or impure capacitors are not free from dielectric loss. If they are not free from dielectric loss, it is impossible to obtain balance condition. Okay, so this bridge can be used for the measurement of capacitance for impure capacitor, for pure capacitor. Okay, so let me make statement like this. This bridge cannot be used for the measurement of capacitance. Okay, for the measurement of capacitance for impure capacitor. This bridge can be used only for lossless capacitors like air capacitors. Measurement of capacitance for air capacitors can be used only for lossless capacitors like air capacitors. Okay, so air capacitors can be compared in this bridge. Okay, so this is the limitation of this bridge. It is impossible to obtain balance if both capacitors are not free from dielectric loss. Okay, here these two are pure capacitors. Okay, this method is applied only for pure capacitors. Pure capacitors can be compared in this method, in this bridge. Okay, impure capacitors cannot be compared, and it is impossible to obtain balance conditions if you use impure capacitors in this bridge. Okay, if you use impure capacitors in this bridge, impure capacitor is not free from dielectric loss. Okay, advantage of this bridge is simplicity. Okay, now let us draw the phasor diagram. Okay. Now let us take current as reference vector. Anyhow, I1 is current flowing, I1 is the current which is flowing to this. So let me take current as reference vector. So let this is I1. Okay. Now I1, how can I draw E3? Anyhow, I1 is equal to I3. So I1 is equal to I3. Okay, otherwise let me write I1 only. Here you can write I1 is equal to I3 and I2 is equal to I4. You can also write over here. Okay. Now voltage across this in phase with I1 or I3, right? So now sorry. E3, I3 R3. Okay, so this will be I3 R3. I3 R3 in phase with I3 R3 in phase with I1. So this will be I3 R3. I3 R3, which is nothing but E3, which is nothing but E4, which is nothing but I4 R4 or I2 R4. So this is I2 R4, this phasor is I2 R4 or I3 R3, right? Okay, now how can I draw I2? If this is I2 R4 means this will be I2. So I3 R3 will be in phase with I1 and I2 R4 will be in phase with I2. Okay, so this will be I1 comma I2. Okay. Now how can I draw the voltage across this capacitor? Voltage across that capacitor lags current by an angle 90 degrees. Okay. So this will be what? Sorry. This will be what? Voltage across capacitor. That is E1 is equal to E2 is equal to I1 by omega C1 is equal to I2 by omega C2. Okay. Now phasor sum of E3. Okay, let me write over here. This is what? I3 R3, this is E3, E4, I2 R4, right? Okay, now phasor sum of these two, phasor sum of this, okay, phasor sum of E3 and E1 is what? Phasor sum of E1 and E3 is E. Right, so this will be E. This will be E. Okay. Here it is not impossible to obtain balance condition if both capacitors are not free from dielectric loss. Okay, that is If these two capacitance are impure capacitance, this method cannot be applied, this bridge cannot be used. Okay, so for the measurement of capacitance, in case of impure capacitors, we use another bridge, that is modified de Sauty's bridge. Okay, to overcome this limitation. Okay, this bridge can't be used for the measurement of capacitance for impure capacitor. Okay, to overcome this limitation, we are going to have second bridge, that is modified de Sauty's bridge. Okay, modified de Sauty's bridge, modified de Sauty's bridge. Okay, well, this is modified de Sauty's bridge. Okay, this is modified de Sauty's bridge. Okay, this is R3, this is R4, and this will be R1 C, capital R1, capital R2, and this is C2, this is R2. Okay, anyhow, voltage across this will be E1, voltage across this is E3, voltage across this is E2, and voltage across this is E4. Okay, let I1 is the current flowing to this, I3 is the current flowing to this, I2 is the current flowing to this, I4 is the current flowing to this. Okay, here this is EC1, that is voltage across impure capacitor. This is impure capacitor. Series combination of this capacitance and resistance is impure capacitor, C1. This is another impure capacitor. Okay, voltage across this will be EC2, another impure capacitor. Okay, the series combination of these two is nothing but impure capacitor. Placing impure capacitor is nothing but placing series combination of capacitance and resistance like this, in series combination like this. Okay, this is the impure capacitance, this is impure capacitance, this is the resistance which is connected in series with this impure capacitance, this is the resistance which is connected in series with this impure capacitance. Okay, two impure capacitances. Okay, this impure capacitance is the combination of capacitance and resistance, this impure capacitance is the combination of capacitance and resistance. Okay, this series combination is impure capacitance. Similarly, this series combination is impure capacitance. EC1 is the voltage across this impure capacitance, impure capacitor. This will be impure capacitor. Okay, now under balanced conditions, we know Z1, Z4 is equal to Z2, Z3. Okay, so what is Z1? Z1 is equal to R1 plus R1 plus 1 by j omega C1. Z4 is R4, which is equal to, what is Z2? Z2 is R2 plus 1 by j omega C2 into what is Z3? R3. Okay, now j omega c1 r1 r4 plus j omega c1 r1 r4 plus r4 by j omega c1. Yeah, which is equal to j omega c2 r2 r3 plus j omega c2 r2 r3 plus r3 by j omega c2. Both will get cancelled. Okay, then we are going to get j omega c1 c2 r1 r4 plus j omega c1 c2 r1 r4 plus r4 c2 is equal to j omega c1 c2 r2 r3 plus j omega c1 c2 r2 r3 plus r3 c1. Okay, equate both real and imaginary parts. Imaginary parts separately, then you are going to get this c1 will be equal to, okay, after equating both real and imaginary parts, okay, otherwise you can see this is real part and this is real part. Okay, so r4 c2 is equal to r3 c1. From this, c1 is equal to r4 by r3 into c1, sorry, into c2. Okay, if we equate both, if we equate imaginary parts on both sides, then you are going to get small r1 is equal to r3 by r4 into r2 plus small r2 minus r1. You are going to get this. Okay. Now coming to D factor or dissipation factor, which is equal to tan delta, which is equal to omega c1 r1 is the dissipation factor. Okay, here dissipation factor is omega rc. Okay, so here R1 is the resistance of this capacitor. Okay, resistance of this impure capacitor, right? So dissipation factor will be omega R1 C1. So omega R1 C1. In the next class we will discuss about shearing bridge. Thank you.